Okay, so this is very much the final step of our journey in terms of how we evaluate somebody for endurance and looking at their endurance physiology. And what we're going to address in this session is something referred to as critical power. You might read to it as critical speed or even critical velocity. And we're going to understand what critical power is, and actually in many ways this is the bit that ties all the pieces together. And you could argue to a certain degree that you've gone through the course of this module and have been collecting pieces of a jigsaw, but not quite knowing where they all fit together. Critical power really does, I think, tie everything together and offers us a phenomenal insight in terms of our endurance physiology. But we're really unable to get to this stage until we understood all those other components that came together, because it is a composite of our understanding of VO2 max, oxygen kinetics, blood lactate responses. All of those are needed in terms of our understanding of this component. And then we're going to then look at how we assess this and then move into the idea of its significance in terms of endurance performance. Now, to do that, we first of all need to go back a little bit in terms of basics, and we need to go back and just think about the relationship between power and time. And again, don't view power as being some high intensity thing. Remember, you can have power outputs from 1 watt all the way up, so it could be from low power outputs to high power outputs. But we need to understand that relationship, because that relationship is universal. So this isn't just an exercise based relationship. That relationship is the same throughout nature. That relationship in terms of power and time is the same whether you are a human through to a dolphin through to a crocodile. The same thing applies. Then we're going to look at how we can extend this relationship to the concept of fatigue. Now, this is fundamentally very important, because what we need to understand is, if we know why there's a relationship between power and time and what it is, we then can start to understand that there must be a point in that relationship where the power output cannot be sustained for a prolonged period of time, and anything below that point can be sustained almost indefinitely. So that's a really important notion we have to address. And then finally, we're going to look at the rationale for assessing critical power and the protocols that are available for us to do this. And that's, again, a really important section, and it lays bare this idea that we've dealt with in previous sessions of the validity and reliability in the test that we're going to use, and how we pick the right test for the job. So let's start by defining what we mean by critical power or critical speeds. This is in a paper by Hill, which was published in the European Journal of Applied Physiology, and Hill merely defines it as the highest submaximal exercise intensity that can be sustained without eliciting VO2 max. Now, if you've watched the previous podcast on oxygen uptake kinetics, I suspect this is really suggesting to you about an exercise domain that this may appear in. We know that if we're in the severe exercise domain, that quite clearly VO2 will drift towards its max. So if we are in severe domain, we can't sustain this. It's not sustainable. So this does suggest to us that we are probably almost certainly going to be in the heavy exercise domain. And critical power sits somewhere in the heavy domain. But the key thing is that it's an intensity that can be sustained. Now, what you have to clear in your minds here is, it is not like identifying lactate turn points where we're looking for a lactate concentration, or it's not like identifying VO2 submaximum where we're looking for a VO2 response. This is where the power output may well be held firm and fixed. That's critical power or critical speed. But actually, you may well be getting quite acute biological responses, but the key is they are tolerable biological responses, despite the fact the power output is being maintained. So one could anticipate that if we were in the heavy domain, which this is alluding to, that quite clearly lactate concentration is going to rise and VO2 is going to be rising over the course of that exercise bout. But the power output is the highest sustainable power output that can be maintained without drifting towards VO2 max. The original definition actually came from some work back in 1965, and although it wasn't generically aimed at exercise in that point. It was published in the Journal of Ergonomics. Monod and his co-worker Scherer really pinpointed this biological construct of critical power and argued that it's the amount of work a muscle can do before being exhausted. And they suggested it's the conditions of a fatigueless task. Now, actually, in many ways, if we think about that idea of a fatigueless task, that's quite compelling, isn't it? And actually, this gets again to the heart of what we mean by fatigue. You can be fatiguing, but still carry on exercising. So this is the idea that you're doing a task that can be sustained. You will have the artifacts of fatigue, so you might have raised hydrogen ion concentrations and low intramuscular pHs and raised blood lactate scores and decreased glycogen contents, but you can still exercise in that state. You have not hit the point of fatigue. And in fact, what we know is that exhaustion is the accumulation of all those fatigue-like responses. And so what they're referring to here in terms of critical power is it's the amount of work that can be done before you hit exhaustion. But it's the amount of work that can be done where fatigue is not overwhelming. And if we go back to the Hill definition, and we think about the idea of sustained exercise intensity before eliciting VO2 max, we can see why now it can't be in the severe exercise domain, and it's got to be in the heavy domain, because if it was in severe, then quite clearly fatigue rises to VO2 max, and we are going to hit that point of volitional exhaustion. Here, when we are working in the heavy domain, which is what it's suggesting for critical power, then that can be sustained for quite a long period of time. So we've got a definition of what it is, but at the moment it probably feels quite nebulous to you, and perhaps you're not seeing what it is, and actually as you see it pictorially, I think it makes an awful lot more sense. But in order for us to address this, we need to go back historically, and we've come across these guys before. This is A.V. Hill and his colleagues Long and Lupton, and in fact this is the same from one of the same set of papers where they won the Nobel Prize for understanding oxygen consumption. This one actually was to do with muscular exercise and lactic acid, which again they won part of the Nobel Prize for from some of the work they did with a German colleague, which is Otto Meyerhoff. But actually this data set here is quite fascinating. Notice what it's suggesting to you. It's suggesting to you on the x-axis we've got speed, and on the y-axis we've got oxygen consumption, or oxygen requirements as they refer to it here. And you can see quite clearly that as the speed increases, irrespective of who the individual is, so does the oxygen requirement. But notice that that relationship is in by no shape or means linear. That in fact what you have got is what appears to be an exponential relationship. And actually that relationship is very much at the heart of where we are going to go in this session today in terms of understanding critical power. That we are not dealing with linear relationships in terms of our understanding of the way in which power outputs are sustained. And this work here, although nearly 100 years old now, really did set the benchmark in terms of understanding why we have changes in energy turnover in relation to changes in speed, and the fact that this relationship is, as I say, non-linear. So I would like to now draw your attention to this very nice paper from Annie van Hattelo. Now Annie's based down in Exeter under the guidance, well originally under the guidance of Andy Jones, but she now is a senior lecturer down there. But her background is all to do with critical power. And she writes this really nice statement for us that we can see here. Let's just go back. So she states this: on the basis of the characteristic blood lactate and oxygen uptake VO2 responses during constant work rate exercise, three exercise intensity domains are being defined, which we've seen in previous podcasts: moderate, heavy and severe. The boundary between moderate and heavy domains can be established during incremental exercise testing using the lactate threshold or the gas exchange equivalent, the gas exchange threshold, which again we've seen on previous podcasts where we've looked at ventilatory thresholds and blood lactate transitions. The boundary, however, between heavy and severe exercise signifies the highest work rate at which a steady state can be attained. Work rate above this boundary results in VO2 and blood lactate rising as a function of time until the VO2 peak is attained. So let's think about that. We can see in the first paragraph what we've seen in previous podcasts, which is there is a boundary between moderate and heavy, which is identified using the lactate threshold or the gas exchange threshold, and then you've got this boundary which is between heavy and severe. And once we go into severe, what we find is that there is a blood lactate and VO2 rise until VO2 max. What does that sound like? It sounds like this. Critical power is the highest submaximal exercise intensity that can be sustained without eliciting VO2 max. So it's tied very nicely to us, although we haven't got to what critical speed really is yet, critical power really is yet. It's certainly got to the point that we now understand that it sits in the heavy exercise domain. So whatever this is, whatever critical power is that we're about to get to, it sits in this heavy domain. Once we go into the severe domain, you must be working above critical power. If you go to the moderate domain, you're working way below critical power.